Welcome to our Quantum Deep Dive. Today, we're exploring the absolute cutting edge of artificial intelligence, a future that could leave today's models in the dust. We're breaking down Jurgoj Schneppot's fascinating work on quantum text generation.
That's right. We're going to explore how the strange, almost magical world of quantum mechanics could fundamentally revolutionize the AI that writes our emails and answers our questions.
Exactly. So first, we'll cover the limits of the models we use right now. Then, we're going to dive into the quantum realm itself to understand the basic principles.
And from there, we'll see how you can actually teach these quantum bits, or qubits, to write. And finally, we'll get a dose of reality about the massive challenges that are still ahead.
Okay, let's get into it.
So, let's start with what we all know. AI models like the GPT family have become incredibly powerful at understanding and generating human-like language. Oh, they're amazing tools! I mean, they can write essays, debug code, even create poetry on demand. But this impressive performance, this brilliance, well, it hides some serious growing pains.
And those growing pains really start with just raw power consumption. The computational demands are just staggering.
Yeah, we're not talking about just plugging in a powerful server here. Training a model like GPT-4 requires millions of hours of GPU time. That's an energy cost that's equivalent to a small city, and a financial cost that runs into the tens of millions of dollars for just one training run.
So this isn't just an economic barrier that prevents smaller players from competing, it's a huge environmental concern too.
Right, and beyond the sheer energy cost, there are fundamental technical limits just baked into the architecture of today's models.
Exactly. The core mechanism in these transformer models is something called self-attention, and while it's incredibly effective, it scales quadratically. You'll see that on the slide as O of n squared.
And what that actually means is that if you double the length of the text you want to process, say you go from a 10-page document to a 20-page one, the computation required doesn't just double, it quadruples. If you triple the length, it takes 9 times the work.
So this makes processing very long, complex documents like legal contracts or scientific papers incredibly inefficient. And because the models are so complex, with billions of parameters, it's often impossible to even know why they produce a certain answer. It creates a black box problem.
So the crucial point here is we're hitting a wall.
And to break through that wall, researchers are looking to a completely different kind of computing, one that operates on the mind-bending principles of quantum mechanics.
And this is a really key point. This isn't just about making our current computers faster. It's about building them from the ground up based on a fundamentally different and, frankly, much stranger understanding of reality itself.
So let's start with the absolute basic building block. You know, in the computers we use every day, a bit is the smallest unit of data. It's just a simple on or off switch, a 0 or a 1. But in quantum computing, the building block is the qubit. And as you can see, it's a different beast entirely. A qubit can be a 0, it can be a 1, or, and this is the incredible part, it can be a blend of both at the same time. This one property, this ability to exist in multiple states at once, unlocks a computational space that is exponentially larger than anything a classical computer could ever hope to access.
This amazing ability to be in multiple states at the same time has a name. It's called superposition.
You know, the best analogy is a spinning coin. While it's in the air, spinning, it isn't heads or tails, it's in a superposition of both possibilities. It's only when it lands, when you measure it, that it picks one definite state.
A qubit is just like that spinning coin. While it's in superposition, it holds the potential for both 0 and 1. And when you link these qubits together, the power just explodes. A computer with just a few hundred qubits in superposition can explore a number of possibilities greater than the number of atoms in the known universe.
And that is the source of what's often called quantum parallelism, the ability to perform a huge number of calculations all at once.
And if superposition wasn't strange enough for you, there's another property called entanglement. This is what Albert Einstein famously and kind of skeptically called spooky action at a distance. Basically, entanglement is when 2 or more qubits become inextricably linked. Their fates are intertwined. So if you measure one entangled qubit and find out it's in a 0 state, you instantly know the state of the other one is also 0, even if it's on the other side of the galaxy. It's not that a signal is being sent faster than light, it's more like they are 2 parts of a single system. And this bizarre connection allows for incredibly powerful computations and totally new ways of encoding the relationships between different pieces of information.
So we have these incredibly powerful new quantum properties, superposition and entanglement, and they're fantastic for things like simulating complex molecules for drug discovery or for breaking cryptographic codes.
But how on earth can superposition and entanglement help an AI write better poetry or generate more accurate code? Well, the answer lies in how we represent the very nature of language itself. Okay, so this is where it gets really fascinating. In today's AI, a word like bank gets assigned a fixed vector, which is basically a long list of numbers that represents its meaning. The model then has to look at all the surrounding words like river, money, First National to figure out from the context whether we're talking about a riverbank or a financial bank. It's a statistical guessing game, and a very sophisticated one, but a guessing game nonetheless. But in a quantum model, that same word, bank, could be encoded into a qubit. And thanks to superposition, it could exist as both the river meaning and the money meaning at the same time, in parallel. The system doesn't have to guess, it can process both potentials at once, and this creates the potential for a much deeper, more fluid, and more efficient contextual understanding right from the very start.
And this table really highlights the fundamental leap we're talking about. So on the left, you've got classical natural language processing, or NLP. Its semantic representation is based on those fixed vectors we just talked about. It processes information sequentially, or in parallel, but at a very high computational cost. And it understands context by measuring the statistical distance between these fixed data points. Now look at the right, quantum NLP. It uses superposition to hold multiple meanings at once. It can achieve exponentially faster parallel processing, and crucially, it can use entanglement to create direct, non-local links between related concepts in a text, no matter how far apart they are. It's a fundamentally different and potentially far more powerful way to handle all the nuance and ambiguity of human language.
So if, and it's a very big if, we can actually get this right, the applications could be transformative across dozens of industries.
Yeah, and we're not just talking about making our chatbots slightly less annoying. This is about creating entirely new capabilities that are simply impossible with the computers we have today.
Imagine automated journalism, for instance. A quantum AI could generate real-time news articles, synthesizing information from thousands of global data streams in a split second. Or think about scientific discovery. An AI could read and summarize every single new research paper in a field, identify patterns that humans might miss, and even generate new testable hypotheses for researchers to go explore. In the creative fields, you could have a true co-writing partner, an AI that could assist an author in generating a novel, perfectly simulating the complex style of someone like Faulkner or Hemingway. Even software development could be revolutionized, with an AI capable of not just writing, but optimizing and debugging millions of lines of complex code with an efficiency we can't even imagine right now.
Now this all sounds like science fiction, and, in a way it is. We have to be realistic.
We are definitely not there yet. Building a fault-tolerant quantum computer that's powerful enough for these tasks is one of the biggest scientific and engineering challenges of our time.
Take this number, 127. That represents the number of qubits in IBM's Eagle processor, which is one of the most advanced quantum chips in the world today. And it is a truly remarkable achievement of science and engineering. But for the kind of complex language task we've been talking about, we won't need hundreds of qubits. We'll likely need thousands, if not millions, of stable, high-quality, interconnected qubits. We are still at the very, very beginning of that scaling journey. And the core technical problems are immense. So first, there's decoherence. Qubits are unbelievably fragile. The slightest vibration, a stray magnetic field, or a tiny change in temperature, what scientists just call noise, can cause them to lose their delicate quantum properties in a fraction of a second, completely destroying the computation. Then there's error correction. With a classical bit, if you're worried about an error, you just make a few copies and compare them. But a fundamental law of quantum mechanics, the no-cloning theorem, says you can't perfectly copy an unknown quantum state. This makes finding and fixing errors incredibly difficult. And finally, even if we build the hardware, we can't just run today's AI software on it. We have to invent entirely new algorithms from scratch, a whole new way of thinking about programming that's designed specifically for the quantum world. And there's a really serious flip side to all this potential power. A sufficiently large quantum computer using something called Shor's algorithm could break most of the encryption standards we rely on today. And we're talking about the encryption that protects everything: your online banking, corporate data, military communications, government secrets. It would all become vulnerable. That threat is so real and so imminent that a whole new field called post-quantum cryptography is already in a race against time, trying to develop new encryption standards that are safe from attack by both classical and quantum computers.
Which brings us to a final, pretty provocative thought. We've explored the what and the how of quantum text generation, but the ultimate question might be about the who, or maybe the what.
If we succeed in creating a machine that doesn't just mimic language by statistically predicting the next word, but truly understands context and ambiguity through the fundamental laws of quantum physics, what have we actually created? Will it just be a more powerful tool, or will it represent an entirely new kind of intelligence?
And that concludes our deep dive into the incredible potential of quantum text generation. The path ahead is long, and it's filled with enormous challenges, but the destination could redefine our relationship with technology and with language itself, all based on the comprehensive work by Jurg Oesch-Nepat.
Thank you for joining our Quantum Deep Dive. For more information on this topic, please visit schnippet.de. Goodbye.
Schnepat.de is a private project by Jurg Oesch-Nepat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.